Hello, welcome to By Excellence Tutorials. Have you subscribed to the YouTube channel yet? If you have not yet subscribed to the YouTube channel, I ask you to subscribe and click on the notification bell so that you get notified each time I upload a new video. Now, in this video, I'm going to derive with you the unit vectors in polar coordinate system. Because in polar coordinate system, we see that we have the position R and the rotation that are changing with respect to time. So now we are going to solve together, to derive together the unit vectors in polar coordinate system. And also we are going even to derive or to find the derivatives of these unit vectors, meaning once we differentiate these unit vectors with respect to time, what do we get? That's what we're going to do in this video. And in the next video, we are going to use whatever we are going to do in this video and apply them into deriving the velocity and acceleration in polar coordinate system. So I have a system with me and the particle P that has been projected here. By the way, this is just a simple way of deriving this, okay? So I have a two-dimensional system and I have a particle projected there, particle P, okay? So this particle P is subjected to X and Y coordinates and subtending the angle theta, okay? So if this is the angle theta and we have the position vector R, we are going to see that using trigonometric functions, we are going to see that in this case, we are going to have the magnitude of R multiplying by the cosine angle or the cos theta. That will be in the X direction. So we are going to have, this is the magnitude cos theta. That will be our X. And our Y is going to be R sine theta, like that. Okay. So now, where is the unit vector for the position R and the angle theta? So we see that the position R, when theta is constant, is going to increase in this direction. Okay, so it's increasing in that direction, and that will be our unit vector R. And theta will be increasing in this direction. So the unit vector for the rotation is going to be actually perpendicular to the unit vector R. Okay. So theta is going to have a unit vector perpendicular to R. Okay. So we have that now. Now, we know that from the Cartesian coordinate system, we have R being equal to X, I, this is the unit vector, and Yj. Okay. So we can quickly substitute our X is R cos theta, we have our Y, and our Y there is R sine theta, and we have our J there. So this is the position vector. So if this is the position vector of a particle P at any given time T, what we're going to see is that the small change in the position with respect to R, which is the magnitude, at constant theta is going to be a vector tangent. It's going to be a vector tangent to this curve. So what we are saying is that the unit vector R in this case is going to be the small change like that, divided by the magnitude. This is the definition of a unit vector. So now we need to differentiate the position with respect to its magnitude. Okay, so we have r cos theta plus r sin theta. So if we differentiate that, we are going to have, this is simple calculus. Here we are just differentiating r. And once we differentiate r here, we're going to have cos theta, right? And here we're going to have sin theta, j. Okay. So now we can as well find the magnitude of this, and the magnitude of this derivative is basically going to be cos theta squared plus sin theta squared. And this from trigonometry is basically equal to 1. Okay, so we are going to have our unit vector r being equal to cos theta I plus sin theta j. Divided by 1 is basically the same. So this is our unit vector r. Now it is the same thing that happens also to the unit vector in rotation. When in the first place, theta was constant as r was increasing, as the position was increasing. So now in this case, what we are going to have is the position is going to be constant, and theta, the rotation, is going to be increasing. So as theta is increasing, what we are going to have is the unit vector rotation is going to be change in r, change in small change with change in theta, and then we divide by the magnitude. Okay. So now what is the small change in theta? Okay. What is the change of r with respect to theta, rotation? So what we have here is, we'll say we have our position, which is, where's our position? Which r cos theta plus r sin theta. Okay, so this one, when we differentiate this with respect to theta, what we are going to have here, the derivative of cos theta is actually negative sin theta. So we are going to have negative r sin theta I, and the derivative of sin theta is positive cos theta. Also we have r here, j. So we can even say we have r negative sin theta I plus cos theta j. So I've factored out r. Now, what is the magnitude of this change in rotation? So the magnitude here, we have the magnitude to be, okay, sorry. So we have negative r sin theta So this is squared. So I dot I is 1. That's why I've not included it, or I'm not including it. And then we have r cos theta. And this is also squared. So this is going to give us theta squared, like that. And then this is raised to that. So what we are going to have is that this part is actually 1. And then what we're going to have is r. Okay, so the magnitude is r. Now we come to this part now, where we substitute. So how do we substitute? So we have unit vector being given by change in position with respect to the angle. We have r minus sine theta I plus cos theta j. Okay, divide by the magnitude which we have found to be r. So r and r goes, and then we have negative sine theta I plus cos theta j. So this is how we derive, or we come about the unity vectors. Now in the next video, you are going to discover that we are going to be deriving, or we are going to substitute, we need to substitute where we are going to have something like that. And this basically means the change in that unity vector with respect to time. Now, how do we find that? Okay, a lot of people have difficulties in knowing where this comes from. Okay, so now we are going to do the same. We're going to derive that.